Hello, Luke. Welcome to Lesson 84. So today we're going to be talking about a couple of things. We'll be talking about the multiplication of radicals, and we'll be doing some more work with functions. Kind of a continuation from, or even a reinforcement of a previous lesson that we did on uh, functions and evaluating functions and all of that. So let's get started with the multiplication of radicals. This is going to be very straightforward. We're not going to spend a lot of time on it. We're just kind of making official something that you've probably already gathered by the work that we've done with radicals in the past. So if I give you a radical, let's say it's the square root of 12, and I ask you to simplify it, what would you do? Well, hopefully you said that you would take that 12 and you'd break it down into its prime factors. And once you know its prime factors, we would recognize that the square root of 12 could be written as the product of the roots of all the factors. So the root of 2 times the root of 2 times the root of 3, right? And then we can recognize that the square root of 2 times the square root of 2 is simply going to be a 2, right? Anytime we have that, where it's the square root of a number and it's being multiplied by the square root of the same number, we just lose the square root, right? So we have 2 multiplied by the square root of 3. And that would be our simplification for the square root of 12. All right, so this is something that we've been doing for a while, and we've kind of just implied that, yeah, you can multiply square roots. We can take a square root of 2, and we can multiply it by a square root of 2. And we can take, another square root of 2 and multiply it by a square root of 3. All right, we can multiply them. Today, we're just going to kind of make that a little bit more official. So let's say I have 3 times the square root of 7, and I multiply that by 4 times the square root of 11. All right, can I do this? And if I can, how would I do it? So maybe just take your best shot. How could you multiply this out? Well, if you think about it, this is all multiplication. We have 3 times the square root of 7 times 4 times the square root of 11. And with multiplication, there really isn't any order of operations. We can mix and match these as much as we want. We can multiply them in any order. So I'm just going to rearrange these so that it just makes this a little bit more clear. I'm going to put kind of these lead coefficients, I'll call them, first. So I'll have 3 times 4, and then I'll put my radicals. We'll have the square root of 7. And of course, this is all being multiplied by each other, right? And if I set it up like this, it becomes pretty clear that I can easily take this 3 and multiply it by the 4. There's no problem there. So 3 times the 4, that's going to give us a 12. So the question is, can we multiply these two radicals? And the answer is yes. In the same way that we were able to multiply them up here, we're going to take that square root of 7 times the square root of 11, and it just simply becomes the square root of 77. So we just multiply what's underneath the radical sign. And then we keep the radical sign over that. All right, very straightforward. Okay, now sometimes we'll multiply these out and then maybe we can do some simplifying or that kind of thing. But in this case, that's as far as we can go. So that is how you multiply radicals. It's as simple as that. So maybe let's just give a couple more here just for practice. If I have 2 times the square root of 7 times 8 times the square root of let's say we'll go 10. And then times 4 times the square root of, let's try a square root of 24. Make it a little interesting here. Okay, so let's go ahead and multiply that out. Try it on your own first, and then we'll do it together. All right, so again, we will just start by kind of multiplying all of our coefficients. All right, our numbers outside of the radicals. So we have 2 times 8 is 16. 16 times 4 is what? 16 times 50. 16 times 4 is what? 64. Yeah, 64. So that's just our coefficients. Now for our radicals. So we have the square root of 7 times the square root of 10 times the square root of 24. Before I actually multiply these out, maybe I'll write them. Square root of 7 times the square root of 10 times the square root of 24. It's actually a good idea to look at these and just see if you could simplify them any more. Okay, square root of 7 we cannot. It's already broken down into its primes. The square root of 10, you might think you could, but if you think about it close enough, you know, the square root of 10, you break that down into its primes, it's just a 2 and a 5. And since there isn't any duplicates in there, that's as far as we can go to reduce it. And then the 24, now that one we can. So if we take the 24 and we break that down into its primes, we find that we do have some 2's in here that are duplicates, right? So remember, for every pair, we can just kind of think of that as pulling that out as a single 2. So this kind of translates into a 2. Because remember, these are all, you know, we should think of these as square roots of these numbers. So the square root of 2 times the square root of 2, well, that's just going to combine to give me a 2 without the square root, right? And then I'll have left these 2 here. That's just going to give me a square root of 6 left over. So I end up with 2 times the square root of 6. Right? So this 24, the square root of 24, is actually going to become 2 times the square root of 6. And once again, I'm just going to rewrite this, but I'm going to write this coefficient first. So it'll be 64 times 2 times the square root of 6, and I still have the square root of 7, and I still have the square root of 10, all being multiplied here. All right? But now I can multiply the 64 times the 2, which is going to give me 128. And now I can say, well, what's 6 times 7? That's 42. 42 times 10 is 420. So I end up with the square root of 420. Now, I could now look at that 420 and decide whether or not that could be broken down any further. And in this case, let's find out. So 420, take the prime factors of that. A 2 can go into it, 210 times. A 2 can go into it again. So there you go. We've already got a duplicate, which is going to be 105 times. This is going to be a 3, which is a 35. Believe 35. We can do another 3 and get. I'm sorry. No, we can't do another 3. We can do a 5. My brain is not on today. We can do a 5, which will give us a 7. All right. So we do have a pair of 2's that we could pull out. So we still have this 128. But now we're going to multiply it by 2 that we pulled out. And then we still have a 3, 5, and a 7 underneath the radical. So 3 times 5 is 15. 15 times 7 is 135. No, 105. My goodness, 105. So we end up with times 2 times the square root of 105. And now we can multiply these two coefficients again. So 128 times 2 is going to give us what? 256. 256 times the square root of 105. Whew. All right, there we go. So that is not only the product of these radicals here, it's also the simplified product of those radicals. Okay, so hopefully that makes sense. Should be pretty easy. Okay, now we need to talk about functions again. Okay, so we talked about functions in the past in a previous lesson. We're going to review that a little bit today and then talk about the differences between a function and a relation. Okay, and I think to begin with, we'll start with just talking about relations. Okay, which we did not talk about in our previous lesson. So when we think of relations, we're just thinking of correspondences. We're thinking about mappings, you might say, from one set of items to another set of items. So, for example, if I have in this first circle the 2, 6, and 8, okay, that's a set of items, all right? And then you can see I've mapped it to the second circle, which also has a set of numbers in there. And the 2 gets mapped, or you might think of it as gets connected to, or it relates to the 4. So the 2 relates to the 4, the 6 relates to the 36, and the 8 relates to the 64. Okay? That's all a relation is. A relation just simply means you have one set, and for each member of that set, it's related to something else in a different set. Okay? And that's really all there is to it. There aren't a whole lot of rules for relations, other than each number in this set, or each item in this set, has to have a relation in this set. Okay, that's really the only rule. Okay, so does everything in here have a relation over in this set? Yes, they do. Therefore, this is a relation. Okay, very simple. That's all it is. And again, it doesn't have to be numbers. I mean, you could have, symbols, maybe punctuation, for example. You have all of these things here. And maybe that's related to the English version. Maybe it's, a semicolon is one thing over here. Maybe a period is here. Exclamation point is here. Okay, and therefore, so the semicolon would have a relationship with this semicolon, the English version. The period would have a relationship with the period. The exclamation point would have an relation with exclamation point. We would need one more in here, though, to make it a complete relation. We'd have to put a comma here because we have a comma over here, and that hasn't been related to anything yet, so that has to come over to here. All right? So this would also be considered a relation. Okay? In a way, you can kind of think about writing these in ordered pairs. You can kind of think about saying, okay, the 2 is in the one set, the first set, and it relates to the 4. So you might think of it as an ordered pair. 2 goes with 4. This is the way you'll often see it. 2 goes with 4. The 6, well, the 6 would be another point of relation, and where would that 6, or what would that 6 be related to? A 36, right? And then I've also got an 8. What would the 8 be related to? A 64, right? This would be another way to write a relationship. Okay, so I've got this chart, or this graph, this picture, that we're able to visually see kind of what's going on. But you could also just write it as ordered pairs. And these ordered pairs would represent a relationship. Okay? And then same thing over here. I mean, you could write this as a relation. You could say, semicolon, comma. It's maybe a little confusing, but semicolon, right? That would be an ordered pair. And then you could do the rest as well. Okay? So hopefully that makes sense. A relation is not difficult to understand. The one thing that you need to look for, though, is if everything has a relationship. So, for example, if I were to remove these arrows here, okay, and remove this, okay, and then I would say, okay, is this graph, this picture, does it depict a relation? The answer would be no, it does not. Why doesn't it? Because not everything in this first circle here, this first set, relates to something in the second set. The 8 is just kind of all by himself. He doesn't relate to anything. So since he doesn't relate to anything, this whole thing could not be considered a relation. All right? That's really the one thing to look for. All right, so that is a relation. Now let's talk about a function. Okay? Well, first off, let's look at this chart, or this picture, and just ask ourselves, is it a relation? Maybe that we'll start with that. Is this a relation? What do you think? Relation? Question mark? Well, let's think about it. Do we have all of our numbers in this first set being related to another set of numbers in this second set? We sure do. The 3 relates to the 6. The 4 relates to the 7 and the 8. Okay? So there's two relations for him. But he does relate to something over here. And then the 6 relates to the 10. So sure, this would be a relation. Okay? Yes. All right. Is it a function? That is the question now. Is it a function? All right. And to know that, we have to think about how a function works. A function is simply a relation, but it has the added rule, I guess, that for every one of the input, you might say, the domain, we'll call this one the domain, like we learned in the previous lesson, that's the input. For every member of the input, every member of the domain, it has to have one unique corresponding member in the range. Remember, this is the range. Okay? And by the way, this is not only the range, but we can call each one of these individual members of the range an image. Another piece of vocabulary for you. So that would be called an image. All right. So for example, the image of 3 is 6. The image of 4 is 7 and 8. Okay. Now, a function is only a function if each member of the domain has a unique image. In other words, the function domain, any member of that, cannot have more than one image for the same member of the domain. So this 4 has 2 images. It has a 7 and an 8. Therefore, this is not a function. This 4 is what messes it all up. The 3 works out because it has one image for the 3. The 6 has only one image. The 4 has 2 images. Oh, bad, bad, bad. So it is a relation, but it is not a function. Okay? All right, let's try another one here. So what do you think about this one? Is this one a relation? Is it a relation? Answer? Yes, it is. Yes, it is a relation. Is it a function? You tell me. Is it a function? No, it is not. For the same reason as the last one. The 7 works out, it has one image. The 4, however, has 2 images. And therefore, it is not a function. Again, this is the domain. This is the range. And of course, these are all the images. Okay? Put that here. Image. Okay, very good. So hopefully you saw that right away. Let's go to another one. Is this one a relation? Let's start with that. Is it a relation? Relation? And the answer is yes, it is. Why? Well, for the simple reason that everything in the domain is being related to something. It's all being related to the 4, but they are being related to something. So yes, this would be a relation. And this again, whoops, is the range. Now, our next question, you know what it is. Is this a function? All right, now, come on now. Is it a function? What do you think? Yes or no? Think about what we said about functions and whether or not this breaks the rules somehow. The answer is yes, it is a function. All right. Now, you might say, well, wait a minute, they're all going to the 4. Yes, but that's all right. It's okay if they all go to the same number. What's not okay is if one member of the domain goes to more than one member of the range. All right. So in this case, 3 goes to the 4, 6 goes to the 4, 2 goes to the 4. But that's great. There's nothing wrong with that. The 3 does not go to something other than just the 4. It doesn't go to like a 4 and a 5. It just goes to one single member of the range. It has one image. One image. Okay? That's fine. So this would be a function. All right? All right, how about this one? Is this one a relation? Relation? What do you think? The answer is no. I hope you got that one, because that would mean you were paying attention to earlier in the lesson when I said that in order for it to be a relation, every member of the first set has to have an image in the second set. And in this case, the 8 does not. The 8 isn't going anywhere. It's not related to anything. So no, this is not a relation. Is it a function? Well, actually, that question should be really easy. If it's not a relation, it can't be a function. So if the answer to the relation question is no, then you don't even have to think any further. Just simply write no for the function. It has to be a relation first in order for it to be a function. And this is not a relation, so therefore it's not a function. All right? Okay. How about this one? This is kind of an interesting one. We have our domain here, and we have our range here. Okay. And so basically what this is saying is this first set includes all the integers. So think of any integer you'd like that is in here. Okay. And then what are we doing? We're taking pairs of those integers. I'm sorry. We're taking an integer and then we're plugging it in for this x. So we place the integer, whichever one we chose over here, plug it into the x. That produces a y. The y's are all over here. So these are all the y's. Okay. So depending upon what we pick as our integer, that's going to get corresponded, or it'll get mapped to a member of the range, which we're going to call the y, or the image. And so each one of these integers gets mapped to an image in the range. Okay? The difference here is they're actually kind of telling us what the process is. In all of these other ones, I didn't tell you how the 3 got changed to a 2. Or the 7 got changed to a 4. I didn't tell you how the 3 got changed to the 4. I plug in a 3, I get a 4. How does that happen? Well, I didn't tell you. Somewhere in between here, there's like a magic box that these go through, and they change these inputs to outputs. So you input the 3, you get out the 4. You input the 6, you get out the 4. You input the 2, you get out the 4. I didn't tell you how that happens internally. I just told you somehow it does happen. Okay? Here, I'm not telling you what all of these individual images are because there's way too many of them. I wouldn't be able to write all of them in here because this first set includes all integers. That's an infinite number of numbers. So I couldn't put in the infinite number of images, obviously. So instead, I give you the box. I give you the magic box by which we get the y. So I'm telling you, just go ahead and select an x. This is the equation that you're going to use to get the y. All right? And if we think about it, there's no number, there's no integer that I could plug in for x that's going to give me 2 answers. So if I plug in a 3 for x, well, then I get a 5. So if I select a 3, and I plug that 3 into the x, then the y is equal to 3 plus 2, which is 5. So the image is 5. So this 3 is being related to the 5. Could the 3 be related to anything else? Because remember, that's what needs to happen in order for this idea of a function to fail. Is the 3 would, or some other number would have to be related to more than one thing. All right. Could the 3 ever give me something other than a 5? No, I could plug this 3 into this equation as many times as I wanted to. I would always get the 5. I would never get anything other than the 5. So it's pretty clear that that is going to only give me one image. All right. And if you want, just think up a couple other numbers, maybe a negative number. Let's try a negative number. Let's say I got a negative 2, for example. Or maybe we'll go negative 3. We'll go negative 3. All right. I say, okay, I select my integer, negative 3. I plug that in. A negative 3 plus 2, well, that's going to give me a negative 1, right? So that just means that this negative 3 is going to be related to the negative 1. All right. And again, no matter how many times I plug in that negative 3, I'm still going to end up with a negative 1. I'm never going to just suddenly end up with a 5 or a 7 or a 9. It's always going to be a negative 1 when I plug that negative 3 in. That will never change. So it's pretty clear, although it's not proven here, that if you were to pick any integer, plug it into this equation, you would only get one image for that integer. All right. So yes, this would be considered a function. Yes. Okay. And I can, there aren't any integers left out. Any integer in here, I can relate to some, y image over here. Okay. All right. Very good. Lastly, let's talk about a different perspective here. So here, I'm actually giving you the ordered pairs. Now, we kind of talked about this earlier. All right. When we talk about relations or functions, we might think of them as ordered pairs as well. These are very small functions or small relations because they don't have a lot of members, but we can still think of them in this way. So my question would be, for this first set, we have a 4 that's being related to a 3. And, you know, you can think about this as, you know, if in your head, you can think of these circles. The 4 is the domain, the domain. It's being related to a 3, okay? The 3 in the domain is being related to a 6, okay? And then the 7 in the domain is being related to the 2. So we have kind of our x value, we have our y value. That's the relationship. All right? And if we look at that, we could say, is this a function? Because that's the key question. Is it a function? And the answer is yes. So maybe I'll write that up here. Function, question mark. Is it a function? Yes, this would be. All right? They're each being related to one unique image in the range. Okay? All right, this next one. 3, 2, 5, 8, 3, 4, and 6, 1. What do you think? Think about that for a second. Is this a depiction, or is this set a function? What do you think? Well, if you said no, you would be correct. So the answer is no. It is not a function. And why not? Well, think about it. So the 3 relates to a 2. So in your head, you kind of think of those two circles. The 3 goes to the 2. The 5 goes to the 8. The 3 is mapped to the 4. Now, right there, we need to stop and say, whoa, 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 wait a second. I've already said what the 3 went to. The 3 right here, I said went to the 2. And now I'm saying the 3 is also going to the 4. That's a problem, okay? Because remember, in order for it to be a function, that domain has to be mapped to unique members and single members of the range. And here I'm saying the 3 is going to a 2, and then I'm saying the 3 is going to a 4. So clearly the 3 is going to two different images, which means that this cannot be a function. It is a relation, but it is not a function. Okay? All right, next one. Take a look at this one. What do you think? Function or not a function? All right. Well, now here we're saying that the 3 relates to the 3. Or you might think of it, whatever is easiest in your mind to think about. You could say 3 is being mapped to the 3. 4 is being mapped to a 3. And 5 is being mapped to a 3. So here we have a 3, 4, and 5 as our x values, and they're being mapped to the y values, and the only y value is a 3. And all of them are going to that 3. So is this a function? Yes, this would be a function. Because again, they're each going to only a single image. It's the same image in this case, but that's okay. All right, this next one. Look at this one, a 6, 2, 5, 1, 1, 5, 2, 6, 6, 2. Go ahead and think about that one for a second. Is it a function? Well, the answer is yes. It's a function. All right, now you might say, wait a minute, there's something goofy going on in here. There was a 6 going to a 2, and there's a 6 going... Well, I've got two 6s. I've got a 6 for an x value, another 6 for an x value. I thought I couldn't do that. Yeah, and the answer is you can't if they go to two separate images. But in this case, what did we get? We plugged in a 6, we got a 2. Over here, I plugged in a 6, what did I get? A 2. I still got a 2. Now, it's repetitive, I'll grant you, but it's not breaking up the function. I've just done it twice, all right? So if you're to think of your bubbles here, I just have, you know, my x values, which are the 6, 5, 1, 2, and 6. 6, 5, 1, 2, and 6. And then my y values are 2, 1, 5, 6, 2. 2, 1, 5, 6, 2. And the 6 is being mapped to the 2. The 5 is being mapped to the 1. The 1 is being mapped to the 5. The 2 is being mapped to the 6, and the 6 is being mapped to the 2. Now, I might even just erase that last one because it's repeated here. So I might just say, you know, this last one here is just right on top of this one. This 6 going to this 2. We just did it twice, and then we just connected it twice. So that's fine. We can do that. That is A-okay. The 6 is always going to a 2. It doesn't go to anything other than a 2. It's always going to a 2. Okay? Excuse me. All right, so hopefully that makes sense. When they give you these ordered pairs and they ask you whether or not they're functions, remember, the way to do it is just to look at those x's. All right, find all your x's. There's an x. The x is the first number in the ordered pair. And look for duplicates. If they're all unique, like this first one, 4, 3, 7, no duplicates, and they all have a y component, they all just have something out there. I don't care what it is. They just have to have something. Then yes, it's a function. So again, if they're unique x's and the y's are there, well, then it is a function. If, on the other hand, you look through and you find a duplicate, so I found 3 and, oh, I found another 3, a duplicate x. Now be careful, not a duplicate y, a duplicate x. We're looking at x's here. We have a duplicate x, and then look at the y. Is the y the same? In this case, the y is not the same. Then right away you know, no, this is not a function because an x is going to more than one number. All right. Here I could say, okay, what are my x's? I have a 3, a 4, and a 5. 3, 4, 5. They are unique. There's no duplicates. And they all have a y. I don't care what it is. So therefore, yes, it's a function. Here I have my x components. I have a 6 and a 6. I've got a duplicate. It's the only duplicate. I've got a 5 and a 1 and a 2. So the only duplicate is the 6. And I look at the y, but I say, oh, good. The y is still the same. It's 2. So therefore, we're okay. Yes, it is still a function. Okay? All right, very good. So hopefully that makes some sense to you. We'll be working more with this later as well. So make sure that you understand this. We will be building off of it. But I think it's pretty straightforward right now. Do some practice on it in your seat work problems, and then we will see more of this in future lessons. All right, we'll stop here today, and I will see you tomorrow.